All right, guys, we are going digital today with the video. Hopefully this goes well. We'll see. So what I have in front of you here is a graph on Desmos of the function that we found the derivative of yesterday, x squared plus 5. Now the reason I have this graph for us is because, we found the derivative, 2x. I have that written right below it up here. But it's kind of like, well, what does that derivative mean? Like, what does it tell us? Uh, we found it, and we said that if you take any given value of x in this function and plug it in, then that's the slope of that point. But what's the significance of that? So that's what we're going to try to look at today. So I'm going to start with this point right here, 1, 6. I'm going to label the point here real quick. Let's see if it shows up. I got this screenwriting software, and there we go. Now it's working. So we want to take a look at this point right here, 1, 6. In other words, at this point, x is equal to 1. So if we go to our derivative equation, 2x, and we plug in 1, then 2 times 1, of course, is just 2. That means the slope of this point is 2, or 2 over 1. Now, it's good to know that, but we can actually put that into practice, kind of. We can see that by drawing it into our problem here. So what I'm going to do is I'm going to go from this point, and I'm actually going to graph that slope. You guys know slope is rise over run, so I will rise to run 1. So up 2 over 1 puts my next point right there. Up 2 over 1 puts my next point right there. Up 2 over 1, so on and so forth. And I'm going to go backwards a little bit. Down 2 over 1, down 2 over 1, down 2 over 1. So we get this line. And I want to actually graph this line for us. So the slope of the line is 2. That's what we were just doing here. And we see that it crosses the axis at 4. So that's the y-intercept. So y equals 2x plus 4. So I'm going to take the screenwriting down, and I'm going to type in that equation. Y equals 2x plus 4. Now you can see that we actually get this line graphed in here. Now what's really important about this line is that we have a line that is what is called tangent to the function that is graphed. A tangent line is a line that only intersects at a single point. This point right here. You'll notice that before this point, it shoots off in the direction downwards and it doesn't come near our red graph at all. And beyond this point, it strays off to the right of our function. So it connects in one point. And again, this is something called a tangent. The way I remember this is because, we use the term tangent conversationally if a couple people are talking about something and then somebody has a, kind of sort of related topic, but they start talking about it and then it starts to deviate, and it's called them going off on a tangent, right? Like that's the phrase for it. And the reason that is called going off on a tangent is because it is a topic that only connects with the conversation you're having in one exact point. It had that one intersection, but then it deviated and strayed way far away. It got off topic, right? It was going off on a tangent. So that's one way to remember this as tangent, and where we get actually the term for the phrase. So what we're going to do is we see that we just chose that one number and it worked for us. I'm going to choose another number here. I'm going to choose this right here. Now at this point, x equals, what is that, -2? Yeah, x equals -2. So if I go to my derivative, 2x, and I plug in -2 for x, then 2 times -2 is going to be -4. So with a slope of -4, I'm going to go ahead and plot the points here. So -4 means down 4 and then run 1. So 1, 2, 3, 4 over 1. And then in the other direction, 1, 2, 3, 4 over 1. And I'm actually going to minimize this real quick so that I can lower that to get a little bit more of the graph on screen. And then again, 1, 2, 3, 4. All right. So we see these 3 points were in line with the slope of this point. And we have a y-intercept here at 1, and our slope was -4. So our equation should be y equals -4x plus 1. The -4 again from the slope, and the 1 from the y-intercept. So y equals -4x plus 1. And if we graph that and take a look at our points, it's exactly in line. Now I'm going to minimize my my writing here for a second, and we can take a look again at this line that we just graphed. You know, it looks like it's sharing a little more than 1 point there, just because that's about the capabilities that this program has. You know, Desmos has trouble really getting close up and showing there's a difference in that line. But we do notice that this line continues to stray off away from our original function when it goes down towards -infinity, and it strays away from our function as it goes up towards +infinity. And, you know, if we got closer, you see there is that distance, and that distance is growing greater and greater as we zoom in and in and in and in, so on and so forth. So even though it doesn't actually look like those lines are separate whenever we're zoomed out, they in fact are. So no matter where we make this tangent line at, we end up, no matter where we choose our x value of in this equation, if we find its slope, we find out that slope makes a tangent line. So this tangent line is deterministic of the instantaneous direction and, in some cases, velocity or speed of an individual point. So, for instance, if we were working on projectile motion and this parabola was flipped the way that we usually see things move, right? Then we would be able to pick out one individual point along that parabola, much like we did here, and we would discover that at that one point in time, what the direction and the speed of that point is. Now, it's going to take a little while for us to get there, because that's kind of a higher concept, and we got to get the fundamentals of derivatives down first. But that's the idea behind this unit. That's what this unit is trying to get us to do, is to find any given single point in time and determine the direction of that point. And mathematically speaking, or algebraically speaking, that direction is the slope, because we find by plugging any given x value into our derivative that we found what the slope is. It's always going to be a tangent line. It is always going to stray away from the original function around that x point. It will only ever share that one x point. But that is a visual representation of these derivatives. We will continue on with this tomorrow. We'll keep going with, and we'll probably do another practice derivative, and then we will also try to graph it in the video as well. So if you have any questions, let me know. But otherwise, I will see you guys tomorrow.